Okay, in chapter 8.4, we're going to be covering tangent lines and derivatives. So up until this point, we talked a lot about limits, evaluating limits using tables, using graphs, and then using the limit laws with direct substitution by hand. Now we're going to see how these limits give rise to these other things in calculus called derivatives. So just kind of a side note before we start talking about tangent lines and what they are. Usually when I think about calculus, I think about this little triangle. Limits are the foundation of calculus. After that, after limits, we get derivatives, which we're going to start talking about in this section. And then we also get antiderivatives, which after this section, you'll do a lot more with derivatives and find these derivative shortcuts for finding derivatives of functions. And then after you're all done with derivatives, you'll do what's called antiderivatives or integrals. And then a lot of the other stuff you're going to be doing is applications of limits, applications of derivatives, and applications of antiderivatives. So limits are the foundation of calculus, essentially. All right, so starting off here, starting to talk about tangent lines. So you might remember tangent lines from a geometry class. A tangent line is going to be a line that touches the curve at a certain point and has the same direction as the curve at that singular point. So you can see here, we just have this semicircle, and we are referring to point P. We want to know, what is the tangent line at point P? The tangent line, as you can see, touches the circle at that point and has the same direction as the curve at that point. So if you wanted a tangent line maybe right over here, you can see that the curve is increasing. Maybe the tangent line would look something like this at the point. You're essentially imagining that you are on like a roller coaster and the curve is the roller coaster. And the tangent line is the roller coaster car, but it is a straight car and it is going along the curve like a roller coaster. So it's touching the curve at that point and it has the same direction as the curve at that point as well. So a couple other examples here visually. We have this blue curve and we have these separate points, P1, P2, P3, P4, and P5. So P1 and P3 are correct tangent lines. You can see that it touches at the point and it seems to be having the same direction. So you can see that at P1, the curve is definitely increasing at P1, which is why the line is increasing as well. And then P3, it looks like the curve is decreasing at this point, so the line is also decreasing. But then P2, P4, and P5 are not tangent lines. So P2, it's touching the curve, but it does not have the same direction. P5, touching the curve again, but not the same direction. P4 is very close. It's touching the curve, and the line is increasing, and so is the curve. But it seems the direction seems to be off. It seems like the tangent line would be a little bit less steep. The one that I'm drawing in here now, the red one here, seems to be more of the tangent line. So it's close, but not quite. So if you have these notes that you can look at, if you click this link will take you to the a GIF. Let's take a look at it right now. It's a GIF for how a tangent line can move along the curve. So the curve here is the black curve, maybe some sort of high degree polynomial with all those turning points. And then the red line is the tangent line. So you can see that all of these points have their own specific tangent line. And you can see how it's kind of like riding a roller coaster if you're going from left to right, where the roller coaster car is just a straight line. So the further you'll get in calculus, you'll see why some points don't have a tangent line, like a tangent line might not exist at certain points. For the functions that we're going to be going over today, pretty much all of the points that we're referring to will have a tangent line. All right, so those are tangent lines, very important concepts. We'll be coming back to those in a second. So for the next part, we're going to be talking about secant lines. A secant line is a line connecting 2 points on a curve. So pretty simple concept, right? Secant, just a line connecting 2 points on the curve. So let's take a look at this graph. I'm going to switch it. I don't like the one that's drawn on here. Okay, so let's say we have this curve. I like this one a little better. Pretty simple looking curve. So the idea, before we talk about secant lines, the tangent lines, the idea here, the point that we're actually trying to, or the thing we're trying to actually figure out here, is we want the slope of a tangent line. So let's say we're talking about this point right here, which I'm just going to call point R, because we'll be coming back to calling it point R in a second. And let's draw the tangent line. So the tangent line might look something like that at point R, right? It's touching it at point R, seems to have the same direction as the curve at that point. So then the question is how the heck can we figure out the slope of the tangent line when we only have 1 point? So usually when you think slope, you should be thinking slope formula. In order to use the slope formula, you need 2 points, right? x1, y1, and x2, y2. So if you only have 1 point, how the heck can you find the slope of this tangent line? So to do that, what we're going to be doing is we're going to be creating a secant line first. So let's keep point R as point R, and let's create another point, which I'm going to call point S. So let's create a secant line through these 2 points. And the secant line would look something like this. So we could definitely figure out the slope of the secant line, right? We have 2 points now. We have point R and point S. So since we have 2 points, we can use the slope formula and we can figure out the slope of that secant line. The issue is that our tangent line right now does not look like that secant line. They definitely do not have the same slope. So what we want to do, the whole point of this, is we want to use this secant line to approximate the slope of the tangent line. And the way we're going to do it is we're going to hold R still. We're going to leave R exactly where it is. And we're going to take S and we're going to move it closer and closer to R. So when we do that, for example, let's take it and move it a little bit closer. And let's say that that is the new secant line. So imagine motion, imagine like continuous motion here. I can't really draw continuous motion. So S is going to keep on getting closer and closer and closer to it. So once S gets infinitely close right on top of point R, the slope of the secant line will be the slope of the tangent line. So basically the closer and closer that S gets to R will be a better and better approximation for the slope of the tangent line. Right, so let's do it one more time here. Let's imagine that S is right next to R. That secant line is very close to what our tangent line actually is, right? So since we are talking about motion and we're talking about moving along a curve, we're going to have to introduce limits. So I'm going to go ahead and just redraw what I originally had, just so we can have proper notation. So we had our secant line between point R and point S. I'm also going to say, just so we can get our notation down here in a second, we're going to say that point R has an x coordinate of A that we're holding still. And we're going to say that point S has an x coordinate of the variable itself, x, because that's the one we're going to be moving closer to A. So what we can do now is we can use the slope formula, right? So we can do the slope is y2 minus y1 over x2 minus x1, just our normal slope formula. And the x1 and y1 we're going to use, we're going to say point R is x1, y1, which is point A, comma, f of A, right? y1 is always just the function value. And then point S is going to be the variable. It's going to be x, comma, f of x. So remember, this is just x1, y1, x2, y2. X coordinate here is just A and x. And then f of A and f of x. So plugging those into the slope formula, that's going to be f of x minus f of a, the difference in the y-coordinates, divided by x minus a, the difference in the x-coordinates. So difference in the y divided by difference in the x. And we end up with f of x minus f of a over x minus a, right? So this is literally just the slope formula between these 2 points where we just used an x-coordinate of a that we're holding still and an x-coordinate of just any variable x. So once again, the idea here for what we're doing is we're holding r still. R is going to stay where it is, and we're going to move point S closer and closer to point R, which means in terms of the x-coordinates, x is getting closer to a. So as x gets closer and closer to a, the slope of the secant line is going to become the slope of the tangent line. So once again, since we're talking about movement along a curve, that's where we're going to be talking about limits. Anytime you have the word getting closer to or approaching, that's where we're going to introduce limits. So let's click this link right here and let's take us to a better visual than my explanations. So here is pretty similar to a curve I have, a little bit different obviously, but the blue curve is our function, and then the black dot is our point that we called r, where we're trying to figure out the slope of the tangent line. This is the red point is point S. Between them is a secant line. As we move S closer and closer to point R, it gets to be a better and better approximation to the tangent line. And then once the red point gets directly on the black point, it becomes exactly the tangent line. All right, so then the question is, how the heck can we get exactly on top of it? Once again, that is with limits. So we got all this way just to get to our first little formula that we're going to be using. So the tangent line of a graph of a function at point a, comma f of a, whatever those xy coordinates happen to be, is going to have the slope f of x, right? This is what we just wrote down a second ago, f of x minus a. And then we have the limit as x approaches a, because we want x to be approaching a. X is getting closer and closer to a. So long story short, this little formula right here, the limit as x approaches a of f of x minus f of a over x minus a, represents the slope of the tangent line at x equals a. This is also called the instantaneous rate of change at that point as well. So before we do some calculations with it and before we see kind of like graphically what it represents, just kind of think about what this means. This now means that we can actually find the slope at 1 point on the graph. So instead of needing 2 points to find the slope between 2 points, now we're going to find the slope at a singular point on the graph, which is pretty weird because usually we need 2 points, but now we actually don't. Now we can use limits and we only need 1 point. So before we see an example, just so we can kind of get to see this notation first, get to see this derivative notation. Now we're going to use, instead of m for slope, we're going to use this derivative notation. So this is called, what we just saw a second ago, is called the limit definition of the derivative. So we just saw this a second ago. But instead of calling it m for slope, we're going to call it f prime of a. So f prime of x, you read it just like I said a second ago, you read that little apostrophe as prime, and that is called the derivative of the function. So what this actually tells you, f prime of x or f prime of a for this one, it's going to tell us the slope of the curve at x equals a. So when we do this example in a second, when we use this little formula down here at the bottom to actually figure out, to actually find a value, we're going to find the derivative evaluated at the value, which is the slope of the tangent line or the instantaneous rate of change. Later on in this section, we're going to find f prime of x, which is an entire new function called the derivative function. So basically, thinking back to what we've been talking about in math for forever, if you have a function just plain old f of x, and you plug in an x value, that will give you the y value, which is the height on the graph, right? F of x tells you the y value. Now you're going to have a new function, f prime of x, the derivative, which tells you the slope of the function at a certain point. So f of x tells you the y value. F prime of x is going to tell you the slope, the instantaneous slope at a point. All right, so let's go ahead and see an example, because of course there's a lot of notation, a lot of tricky concepts in here. Let's see an example in a graph, so to make it kind of all make sense. So let's say we have f of x equals x squared, and we want to find f prime of 2, and then after we find it, we'll talk about what the heck it actually means. All right, so let's use this definition. So I'm going to write down the generic definition we just had a second ago. F prime of a equals the limit as x approaches a of f of x minus f of a all over x minus a. All right, so now we're going to have a whole lot of things to plug in. First of all, our a is -2. So let's go ahead and plug in a -2 into all of these a's, which there's a lot of them, like you're playing Wheel of Fortune. So it's going to be f prime of -2 equals limit as x approaches -2 of f of x minus f of -2 over x minus -2. All right, so we just plugged into all of the a's. And then lastly, you're just going to substitute in the f of x is x squared. So you're going to write in what your actual function is right here. That's x squared. And then you always just leave x as x. So basically we just plugged in an a -2 into every single a. And then we just replaced f of x with x squared. So now what we're doing is we need to evaluate this, but one more thing we need to plug in for f of -2. So we have the limit, always make sure you're writing the limit notation, as x approaches -2. Let's just simplify that denominator. X minus -2 is x plus 2. Then we have x squared minus, and now let's go ahead and plug in what f of -2 is. We know f of -2 is just the y value, so you're going to plug it in. -2 squared, plug it into the function, gives you +4. So getting to this point here from the original setup, that's super important, because obviously if you don't get the setup correct, you're not going to be able to do anything to get further into the question. So just make sure you plug everything that needs to be plugged in correctly. F of a is always just the y value, so just don't forget to always plug the a value into the original function. And then either way, this is now our setup. So all we're doing is trying to evaluate this limit, right? So we evaluated limits already. You know, to try direct substitution, if you try direct substitution, you will get 0 over 0. Plug in -2, sad face, you get 0 over 0. So we know how to handle this, right? 0 over 0 with a rational function. You factor the numerator and denominator. The denominator cannot be factored, which is fine. The numerator can be factored to x plus 2 times x minus 2. And now you can cancel off common factors of x plus 2. And you end up getting the limit as x approaches -2 of x minus 2. Now you do direct substitution. You plug in -2. That's -2 minus 2, which is -4. So we just found out that f prime of -2 is -4. And before we create the graph and talk about it graphically, because graphs always help in calculus, let's talk about like what this means from the previous page. So f prime of -2 equals -4. That means the instantaneous rate of change for our original function f of x equals x squared at x equals -2 is -4. That also means, same thing, a different way of saying it, is the slope of the tangent line at x equals -2 for our function is also negative 4. So the instantaneous rate of change, you can kind of think of that, not that it's the best way to say it in math terms, is like the instantaneous slope. The slope at a singular point at this point will be negative 4. So let's go ahead and actually look at this graphically. So let's go all the way back up. Our function is f of x equals x squared. That's a quadratic function. Let's go ahead and graph that really quickly. All right, so there's our function f of x equals x squared. I just put some points down to make it a little bit more accurate. So the point that we're referring to, the x value, is negative 2. So let's go ahead and find that on the x-axis. Here it is. Find it on the curve. It is right up here. So the point that this whole thing is referring to, this whole question, is this point right here. So we're saying at this point, the instantaneous rate of change, the instantaneous slope at that point, is negative 4. And that kind of makes sense if you think about it. I'll draw the tangent line in a second here. But you know that the curve is decreasing, right? It's falling left to right, so the curve is decreasing. So it makes sense to have a negative slope because the curve is decreasing. And then lastly, kind of one of the best visuals, is let's draw the tangent line. If you draw the tangent line here, the tangent line, this is not going to by no means be perfect here. If you draw this tangent line, good enough, I guess. Draw the tangent line, it touches it same direction. This tangent line has a slope of negative 4. So actually it looks like I did draw that pretty good. So yeah, that's what this represents visually, conceptually, what the derivative of a value represents. Right, let's see one more example here. And what we're going to do here is we want to find the equation of a tangent line. So this is a very common calculus question where we want to find the equation of a tangent line. So anytime you're creating the equation of a line, more specifically here a tangent line, you're going to write down the point slope form for the equation of a line. So this is just something that you should always have memorized because it pops up a lot in calculus. Point slope form for the equation of a line is y minus y1 equals m times x minus x1. And then as usual, when we are plugging in, we need to plug in x1, y1, and m. And that's going to be x1 is given to us, is 1. y1 does not have to be given to us, but it is. y1 is also 1, because 1 squared is 1. And then m, what the heck is m? M is the slope of the tangent line. The slope of the tangent line is, in thinking about it in the sense from what we just talked about, is always the derivative evaluated at the x-coordinate. So the slope is f prime of 1. That means we need to find f prime of 1. So to find f prime of 1, this is what makes it a calculus-based question. We need to use that little definition. F prime of a is the limit as x approaches a of f of x minus f of a all over x minus a. And we're finding f prime of 1. So we're going to replace all of these a's with a 1. So we have the limit as x approaches 1 of, let's go ahead and just, well, I'll do the denominator, x minus 1 first. And then for the numerator, f of x is the original function, which is just so happens to be x squared again. And then f of a, you could do and say f of 1 for f of a. But let's skip a step. Let's make this a little bit easier. F of a is always just the y value. The y value is given to us, right? The y value is also just so happens to be 1. So once you get comfortable plugging these things in that first step, you can usually just plug everything in one big step. And now all we have to do is evaluate this limit, and that's going to be f prime of 1, which is the slope of our tangent line. So if we try direct substitution, we would get 0 over 0. So that's never going to help. So get used to that. Maybe don't even bother plugging it in because you're always going to get 0 over 0 right away. So what we're going to do, of course, is factor the numerator to x plus 1 times x minus 1. The denominator does not factor. We end up getting x minus 1's cancel, so we're left with the limit as x approaches 1 of x plus 1. Now we do direct substitution, and we get 1 plus 1, plug in the 1, and we get 2. So not that bad, right? Once you kind of get comfortable doing these, it's not as bad as it seems. So now we just found that f prime of 1 is 2. That's the hard part of the question. Now we can go ahead and just plug everything in. So plugging everything in, we have y minus 1 equals 2 times x minus 1. You can leave it like that. That's point slope form. Just for the sake of graphing it and seeing how this looks like graphically, let's solve this for y. So we're going to solve this for y by distributing the slope 2 and then adding 1 on both sides. So the equation of the tangent line, once again, both of these are technically fine, but I'm just going to use the slope-intercept form. This is the equation of the tangent line for f of x equals x squared at x equals 1. So let's go ahead and graph this. Let's graph our function, and then we'll talk about the tangent line afterwards. All right, so once again, here's f of x equals x squared. We just so happen to use the same function from the previous example. And this question is referring to the point at x equals 1, but we know the y-coordinate is also 1, so we can go right to that point, and that is this point right here, right? So if we drew a tangent line here, I'm just going to draw a really quick one. If we drew a tangent line, maybe, ooh, that's real bad, but let's pretend that's a straight line, it would probably look something like this, right? We can now draw this super accurately because we just found the equation, we just created the equation of this line. So 2x minus 1 has a y-intercept of negative 1 and a slope of 2 up 2 to the right 1, and that means it'll be this line right here. So this is the tangent line, which is y equals 2x minus 1. So that means at the point x equals 1 on the function f of x equals x squared, it has an instantaneous rate of change of 2. So the instant slope at x equals 1 equals 2. Or the slope of the tangent line at that point is also 2. Same thing. Okay, let's move on to the next thing. So we're going to talk about another way that we can think about this little formula that we just created. Before we move on though, you probably notice when we're solving these, since I use the same function here, once you get everything plugged in here, and when you're simplifying this version of this little formula, the way that you do it is different depending on what type of function it is. If your original function is a polynomial, which this one is, right? X squared is a quadratic polynomial, then usually what you have to do is what we just did. Usually you have to factor and cancel common factors in order to simplify it. So for us, just for now, for simplicity here, we're only going to be working with polynomials. If you had a square root function or a rational function or something, you'd have to do something different. Factoring would not work. For us, factoring will work for these questions because we will work with polynomials. Okay, so now what we're going to do here for this next little formula that we're going to create is, this is going to be called the alternative definition of the derivative here, is we're actually going to be doing almost the exact same thing, but instead of thinking it as f of x, x comma f of x getting closer to a comma f of a, we're going to be thinking about it as a distance between the 2 points going to 0. So it's literally going to be almost the same thing. So now, instead of thinking about, we'll still call this one a over here on the left. So this point is still going to be called a. And for that point, we're still interested in the slope of the tangent line. So the whole point of doing all this is we still want the slope of this tangent line at that point. And just like before, we have a second point where we're going to create a secant line through these 2 points. And then we're going to move this point closer to this point. So far you're probably saying to yourself, what the heck? We literally just did that a second ago. But instead of calling this x, where we're moving x closer to a, we're going to be thinking about this as a distance away. And this distance we call h. So if this is a and this is h, that would make this next point a plus h, right? So that second point is a plus h. And now what we're going to be doing is the same thing, except we're going to be thinking about h approaching 0. So we're still going to be moving the second point closer to the first point in order to make the secant line become the tangent line. But instead of thinking about it as x approaches a, we're thinking about it as h approaching 0. So with that being said, that gives us our 2 points here, right? We end up having a comma f of a, and then we have a plus h comma f of a plus h. So a comma f of a plus h comma f of a plus h. The y coordinate is always just f of whatever the x coordinate is. So now, just like before, we can figure out the slope between these 2 points, which is f or y2 minus y1. So f of a plus h minus f of a. So difference in the y coordinates divided by x2 minus x1, a plus h minus a. But this time notice that the a's actually cancel, and all we're left with is f of a plus h minus f of a all over h. So it's literally the same like graphical, if that's a word, graphing concept that we just did, where we want the tangent line at the first point on the left, and we're going to create a secant line, and then we're going to get the slope of the tangent line by moving the right point until it's right on top of our left point. But now we're just thinking about it as a distance h approaching 0. So since we want h to approach 0, that's where we need this limit to come into play. So basically we have this right here, f of a plus h minus f of a all over h, and we're going to evaluate that. We're going to evaluate the limit of it as h approaches 0. And it's the same thing we just did a second ago. That is the slope. That is f, the slope of the tangent line. That is f prime of a. So now we have two formulas that actually tell us the same exact thing. We have, let me scroll back up here. We have this one, right here. Limit as x approaches a of f of x minus f. Well, let me look at this one, I guess. We have limit as x approaches a of f of x minus f of a over x minus a. And now we have limit as h approaches 0 of a plus h minus f of a all over h. And they both tell us the instantaneous rate of change, f prime of a, which is the slope of the tangent line at x equals a. So what I'm going to do here, instead of doing an example with this, let's jump right into the next part. Because you would do this the same way, maybe try one on your own. It would be pretty similar to the other one. But what we're going to do now, just for time's sake and make this a little bit, flow a little bit better than going through a million examples of the other way, let's go ahead and do what we just did. But instead of f prime of a, now we're going to do f prime of x. So basically, let's do the exact same thing. Let me draw the function in. So our function looks something like this. So for the third time today, we're doing the exact same thing. We want the slope of this tangent line at this point on the left. But instead of calling this point a is a specific value. Now we're going to let it be a variable. It can be any variable x. So now our point that we're holding still is going to be x. And then the other point over here on the right that we're moving closer to it is still going to be an h distance away. So this point would now be x plus h instead of a plus h. So basically we're doing the same exact thing, but instead of an a, it can be any variable x. The reason you might be saying to yourself, well, what the heck, that doesn't make any difference. The reason why it's going to make a little bit of a difference here is because now we're going to be finding the derivative function instead of the derivative specifically evaluated at a singular point. So let's do the same thing we were doing. We're going to have our xy, or x1, y1, x, comma, f of x plus h, comma, f of x plus h. So just like what we were doing before, using the slope formula. So we have our slope formula. We're going to calculate the slope between these 2 points. We would get the difference in their y-coordinates, f of x plus h minus f of x, all over the difference in their x-coordinates, x plus h minus x. And just like before, in this case, the x's instead of the a's cancel. We're left with f of x plus h minus f of x all over h. So this little result is a pretty important result. This is something called the difference quotient. So when we do this, just like before, once again, this is probably getting pretty repetitive and maybe a little bit confusing because we have f of x's and h's and a's everywhere. But just like before, we want the distance between them to approach 0 because we're moving the point on the right to the point on the left. So since we want that to happen, we're going to do the limit as h approaches 0 of f of x plus h minus f of x all over h. And now this time, this is going to be give us the derivative function instead of the specific value of the derivative at a certain x value. So far, let me just kind of, before we see some examples here, let me just kind of summarize the 3 little techniques. Okay, so these are the 3 little formulas that we went over, 3 little limit definition of the derivative formulas. The 2 on the left tell you the same thing. These are both f prime of a. They will let you evaluate the derivative at a certain x value, evaluate those limits. They will give you the same exact answer. The way you do that might be a little bit different, but they're going to end up giving you the same exact answer. The one on the right is obviously the same idea as the one in the middle here. But the one on the right, when you're using the variable x, that's going to result in the derivative function instead of a specific number for your x value that you plug in. So let's go ahead and see some examples, and then we'll talk about kind of what it represents. So let's find f prime of x, where f of x equals 4x minus 3. So I'm going to write down the limit definition that we just talked about a second ago. And as usual, make sure you're writing things just like how I write them. The notation is very, very important. So when you're doing this, let me scroll back up to the previous step here. When you're thinking about the derivative as a function, the quickest way to think about it is think about it as the slope function. So the derivative function will let you calculate the derivative at any x value you want. It'll let you determine the instantaneous rate of change or the slope of the tangent line at any x value you want. So you wouldn't have to keep on running through these 2 on the left. You would just have to do the 1 on the right, and then you could plug in any x value you want into it. All right, so let's go ahead and run through this so we can see how it's done. So just like the first couple examples that we did for this section of the notes, the functions we're going to be going over are going to be all polynomials. They're actually going to be a little bit easier. They're going to be linear functions and quadratic functions, only polynomials. If you had different functions, you would solve these different ways, but we're only going to be working on polynomials for now. So also, when you are finding f prime of x here, this is a linear function, right? We know that the derivative tells us the slope function. Think to yourself real quick, what do you know about linear functions and their slope? Linear functions have constant slopes. No matter where you are on this line, the slope is always going to be 4. So let's keep that in mind when we get our answer here. So we have the limit as h approaches 0 of, draw a big old line, put h back in the denominator, put the subtraction back in the numerator, And now this is the part that people tend to mess up. You need to substitute in f of x and f of x plus h. So f of x is always the original function. So that part, hopefully not too bad. F of x is whatever the function is. Just make sure you have parentheses around it. I like to use brackets. So f of x is the original function, which is 4x minus 3. Nothing crazy yet. And then this is the part that tends to get messed up the most, is the f of x plus h. Think about when we did this stuff back in the beginning of the semester. F of x plus h, you're going to replace all of the x's with an x plus h, right? So f of x plus h, in this case, is 4 times x plus h minus 3. So just take a quick look at this. We have f of x plus h over here on the left side, and then minus the original f of x over on the right. Make sure you can get this setup correct. If you can't get this setup correct, everything you do after, nothing's going to work out correctly afterwards. So just always double check, make sure your setup is correct. All right, so when you do this, always keep in mind what your goal is. We're obviously trying to evaluate this limit. Your goal is to do direct substitution. You want to plug in a 0 into all of these h's, because h is approaching 0, not x. You want to do direct substitution. You can't do that until the h in the denominator is gone. If you did this right now, you'd get 0 over 0, which is obviously no help. So basically, your endgame goal here is to be able to cancel this h in the denominator with an h factor in the numerator. That's something to keep in mind. But first, I'll kind of write the steps over here on the right. First, you're going to simplify the crap out of the numerator, which means you're going to distribute and combine like terms in the numerator. So a ton of, well, not a ton in this case, but a couple distributing in the numerator, we end up getting 4x plus 4h minus 3. And then minus 4x plus 3, be careful with the negatives. So not too bad. And now we're going to combine like terms. Here's a huge tip hint for you guys. When we have a polynomial, which we will when we're doing these questions, as your original function, when you combine like terms, that's going to mean that your original function over here is going to cancel. So notice when you combine like terms, you have 4x minus 4x. Negative 3 plus 3, that's going to happen every single time. So we are left with limit as h approaches 0 of 4h over h. Next, you want to be able to cancel. You might have to factor. I'll put GCF and cancel the h. In this case, you don't need to do a GCF here. You just can cancel h divided by h as 1. So all we're left with is the limit as h approaches 0 of 4. Now you would do direct substitution, but there's no h to plug in for, right? It's just 4. So anytime you have the limit of a constant, there's nothing to plug in for. So the answer is just 4 itself. So we just found out that f prime of x equals 4. So let's go all the way back up to the beginning. And remember what we said in the beginning here? This is a linear function. Linear functions have constant slopes. Since the derivative is a slope function, we should expect the derivative to be the slope of a linear function, which it is. So even though that's a huge shortcut, you cannot use it if you're told to use this limit definition of the derivative. So kind of a side note, when you're doing these derivative questions in calculus, you're going to do these questions first, and then you're going to get into derivatives afterwards. And the derivative shortcuts are going to make this technique seem very annoying, and you won't have to do this technique anymore. For now, you do have to do it. All right, so let's go ahead and determine the equation of a tangent line at x equals 2 using the result above. So we know equation of a tangent line. Right away, we write down the point slope form for the equation of a line. And we need x1 we need y1, we need m. We're told that we're looking for it at x equals 2. Our x1 is the function evaluated at 2. The function is 4x minus 3. So that's going to be 4x minus 3. 4 times 2 minus 3, which is 8 minus 3, which is 5. So sometimes the y-coordinate will be given to you up here. Sometimes it won't. This time it wasn't. And then the slope is the derivative evaluated at the x-coordinate. So the derivative function is just 4, right? There's no x's to plug in, so it's just 4. So we have the equation of the tangent line is y minus 5 equals 4 times x minus 2. And that's the equation of the tangent line. You could circle this. You could solve this for y. If you solve this for y, you end up getting 4x minus 8. Add 5 to both sides, you get 4x minus 3. Notice that this is the same equation as the equation of the line, right? So if you think about why this is, at x equals 2, so at x equals 2, that's going to be right up here somewhere. So the tangent line for a line, a linear function, is just the line itself. So if your original function is a line, then the tangent line is going to be exactly the same no matter what your x value is. Right, so that was with a linear function. Now let's do 2 or 3 more examples where it's a little bit trickier. Let's see this quadratic function, and you'll see why it's a little bit trickier when we do it. So we want to find f prime of x for f of x equals x squared plus 4x minus 2. So we write down the limit definition of the derivative. Okay, so we write it down, and then we start to fill everything in. So as usual, make sure you always write down the limit notation until you do direct substitution. And I always start these off the same way. Rewrite the limit notation. Draw a big old fraction symbol because you're going to need it to be big. Keep the h in the denominator. Put the subtraction symbol back down here. Plug in f of x over here on the right side. Make sure you have parentheses or a bracket. And I always start this way because that's kind of taking care of the easier things. So before you do anything else, make sure you can get this correct. And now for the last part is the hard part, f of x plus h. So f of x plus h, as always, is going to be the original, but you're going to replace the x's with an x plus h in parentheses. Right? So this is f of x plus h right here. So we can take that and plop it in. I like to put it in a bracket. Technically, you don't need a bracket around f of x plus h. So it's x plus h squared plus 4 times x plus h minus 2. And then you take a look at it, double check everything before you continue, because if you get this wrong, nothing is going to work out the correct way afterwards. So we have f of x plus h minus f of x. So it looks good. And then just like the previous one, we're going to do the same thing. We're going to simplify the numerator by distributing and combining like terms. So distributing, there's a few distributings that we have to do. We have to distribute this -1. We have to distribute this 4. And then unfortunately, it's not that bad, but x plus h squared. So remember, x plus h squared, worst case scenario, you might have to do x plus h times x plus h and distribute it on the side. But remember the shortcut. If you have a binomial squared, it distributes out to the first one squared plus the second one squared plus 2 times both of them multiplied together. So we can use that little shortcut. I recommend using it. So x plus h squared is going to distribute out to x squared plus h squared plus 2xh. And then everything else is a little bit easier. Distribute the 4, that's 4x plus 4h minus 2 minus x squared minus 4x plus 2 after we distribute the -1 all over h. So that the whole numerator is completely expanded, right? Everything is distributed. There's no more parentheses. Now we're going to simplify. Remember, every time this is a polynomial, it will completely cancel off. x squared minus x squared is gone. 4x minus 4x is gone. Negative 2 plus 2 is gone. That'll happen every single time we're working with a polynomial. And we have limit as h approaches 0. We have h squared plus 2xh plus 4h left in the numerator. And this is a lot better now, right? So now for the numerator, let me just write the steps on the right again. So we distributed in the numerator and combined like terms, which canceled the like terms. So now we want to cancel the h. Every term in the numerator will have an h as a factor. So now we can GCF. Technically, you could cancel off an h from every term in the numerator right now if you want to, but let's GCF an h in the numerator. If you factor out an h in the numerator, you're going to be left with h plus 2x plus 4. Now you can do h divided by h cancels, and then the last step is going to be direct substitution. I just like to rewrite it one more time. Limit as h approaches 0 of h plus 2x plus 4. Just always remember, you're only plugging in to whatever you have approaching a number over here. So you're plugging in 0 only to h. So that's going to be 0 plus 2x plus 4, which gives us our derivative function this time as 2x plus 4. So this is not an equation of a tangent line yet. This is the derivative function. Almost every function that we're going to work with has a derivative function. So we have the next question, use the result above to find the equation of the tangent line at x equals -1. So we know equation of a tangent line, point slope form, y minus y1 equals m times x minus x1. We have our x1, we're told, is -1. We don't have y1. We don't have m. y1 is the function evaluated at -1. The slope is the derivative function evaluated at -1. So the f of the y value, y1, f of -1, go all the way back up. You're going to plug in -1 into the original function, x squared plus 4x minus 2. So x squared plus 4x minus 2. That'll give us 1 minus 4 is -3, minus 2 is -5. And then the slope, f prime of -1, is 2 times -1 plus 4, which is -2 plus 4, which is 2. So now we have everything we need. That's going to be y minus -5, so y plus 5, equals m, which is 2 times x minus -1, which is x plus 1. And technically this is fine. You could usually leave it like this. Let's solve for y again though, just so we can compare it to the graph over here on the right. So distribute the 2. Subtract 5 on both sides. 2 minus 5 gives us -3. And here's our slope-intercept form for the equation of the tangent line. So here's our graph. Here's our original function. I did a real rough sketch, but it's decently accurate, I guess. Here's our original quadratic function. And we wanted to figure out at x equals -1, which was right down here, we wanted to know what is the equation of the tangent line. So it looks like the tangent line might look something like this, right? Obviously not perfect. This is the tangent line at x equals -1. So it looks like this is accurate enough. Obviously, this is not drawn to scale perfectly, but it looks like this could be the line 2x minus 3. Positive slope, y-intercept of -3. Sure, looks pretty good. So also just keep in mind, always remember that the slope of the tangent line is the instantaneous rate of change at that x coordinate. All right, let's see one more, I think, here. So let's find the derivative where f of x equals another quadratic, 2x squared minus 3x plus 1. So we write down our formula, and I put the steps we'll be doing over there on the right as well. So we have our formula. And now we're going to go ahead and plug everything in. So start with the limit as h approaches 0 with a big old fraction all over h. Put that minus sign in there. Plug in f of x is the original. 2x squared minus 3x plus 1. And once again, that's how I recommend you do it, because you take care of vast majority of it. And now you just have this last little part, which is f of x plus h. So we replace all of the x's with an x plus h from the original function in parentheses. And that's what we go ahead and plop on in here. So we have 2 times x plus h squared minus 3 times x plus h plus 1. And now that the setup is good, now we go ahead and do these steps right here. So we're going to do a lot of distributing in the numerator. So limit as h approaches 0 of a huge fraction. And then we're going to distribute the negative 1, just like you always are going to have to do. Distribute this negative 3. And then this is the part that might be a little bit annoying. 2 times x plus h squared. So you cannot distribute that 2 right away. You need to leave that 2 out front. X plus h squared is x squared plus h squared plus 2xh using the shortcut from last time. And now we can go ahead and distribute the negative 3. Minus 3x minus 3h plus 1. Distribute the negative 1. Minus 2x squared plus 3x minus 1. And then we just have to do one more thing before we combine like terms, and that's going to be distribute this 2. So don't let yourself get overwhelmed. I know the numerator here looks pretty messy. After we distribute the 2, we get 2x squared plus 2h squared plus 4xh. There's honestly just a lot of terms, and it looks a lot messier than it is because in the next step, a lot of things are going to cancel. So just make sure you're organized, make sure you write neat. So now we're going to combine like terms. 2x squared minus 2x squared, negative 3x plus 3x, 1 minus 1. So we just canceled 6 different terms. All we're left with is 2h squared plus 4xh minus 3h. Now we're going to do GCF and cancel h. So GCF out and h in the numerator. You'd be left with 2h plus 4x minus 3 all over h. Now we can go ahead and cancel the h. We're left with the limit as h approaches 0 of 2h plus 4x minus 3. And now we do direct substitution. So now we go ahead and plug in our 0. So 2 times 0 plus 4x minus 3. That gives us our derivative function. Put it down here. F prime of x equals 4x minus 3. So once again, the derivative function, this is not the equation of the tangent line. We use it to help you find the equation of a tangent line, but this derivative function now can tell us the instantaneous rate of change at any x value we want on our entire original function, which is actually what we're going to do right now. So let's use this result to find f prime of 0, and then we'll look at what it means over here in a second. So f prime of 0 is 4 times 0 minus 3, which is negative 3. So what does this mean? So when we go look at the graph over here on the right, we can find the x-coordinate of 0. So even though this is talking about the derivative at 0, it's talking about x equals 0, so we can still look at x equals 0, which is right up here. This tells us that the instantaneous rate of change at x equals 0 is negative 3, or the slope of the tangent line at x equals 0 is negative 3. So those both mean the same thing. Negative derivative should make sense because the function is clearly decreasing right here. It's falling left to right. So a negative slope would mean that a negative rate of change, instantaneous rate of change, a negative derivative would mean that the function is decreasing. You could, if you want to create the equation of the tangent line, go for it. But you can see that this slope of this tangent line would also be -3. All right, so this section is definitely a little bit tricky, especially with these longer questions here at the end. Very tedious, but like I said, we're only going to be working with polynomials, which makes it a little bit easier because once you deal with square roots and rational functions, the way you would solve these long questions would get a little bit more annoying. So we only need to worry about doing these steps and it'll work every time. It just looks a little bit messy. All right, so that is it for this section.